Okay, so let's move to the fifth section, which is the stress migration. This atomic migration is due to the stress gradient. So, which means we have a chemical potential of the atom, this chemical potential will be the stress dependent. Means when the atoms locate at the stress field, then we need to modify its chemical potential. So this kind of stress gradient will also induce the mass transport. So in order, before we talk the detail of physical concept of the stress migration, then probably I'm going to use this example to show you the presence of the stress gradient. So what we have here is you just try to boil the water. And in the beginning, we are going to fill some water in this water pot, right? And put on this stove and try to heat this waters up. So if we take a look on the wall of this water pot, due to we use this stove, so as you know, if we focus on the wall of this teapot, there's a temperature gradient be acting or be created on this wall, right? The inner part, because you have water, so definitely for sure it will be the lower temperature. Than outer region, you will get a higher temperature. So this wall will be subjected to a temperature gradient on this. So if this, in most of cases, this will be the pure metal, right? So this temperature gradient sometimes, the thickness of this wall is around 1 or 2 millimeters. So probably this temperature gradient will induce atomic flux toward to left-handed side if we assume the heat of transport is positive. And next, my question would be, are there any other atomic flux driven by other parameters try to counterbalance this atomic flux? So probably first thing come up from your mind would be, because there's atomic flux push to more atoms move to the inner wall, so that will cause a stress field inside this material. So the stress field probably will try to counterbalance this effect, right? And under these situations, there's the other driving force you need to consider will be the water vapor. The water vapor will generate a force to counterbalance this, or acting also on this wall, so also to counterbalance this effect. Okay, so this is the reason why we say that when you try to boiling these waters, or when we don't have the water, means that if you forgot to turn off the stove, after you forgot to turn off the stove, then it means there's no water inside this teapot or water pot. Then that may cause some deformation of this teapot after drying. So the reason for this is you are not going to have a water vapor serving a driving force under this situation. Let's probably only have certain forces directly acting on this wall, so that's easy to deform this water pot. So next, I'm going to show you how to quantitatively formulate the potential as a function of stress field or stress. So what we have here is, based on previous description, you know that we need to modify the chemical potential of the atom in the stress field, right? But how to do that? So now we consider interstitials will cause a pure dilation delta omega. And the chemical potential can become like this. This mu1 actually is a chemical potential of atom A in pure materials and or under no stress field. And we need to modify extra term to, this is extra term due to induced by the stress field, right? So in order to formulate this one, so probably I'm giving you an example here. Before there's a stress field presented in your material, the chemical potential for atom A will be equals to mu1. But if this material suffer a stress gradient, for example, like we inserted edge dislocation inside these materials, then this region we can expect it will be due to the addition of this interstitial or these atoms, then that will cause a stress field or a compressive region inside these materials, right? Compressive region. Don't forget, this is compressive region. So how about the chemical potential of the atoms located at this compressive region? You will expect it's larger than mu1 or smaller than mu1. I would say because we perform extra work to insert this atom inside this region, right? So the potential of this atom definitely is larger than mu1. So you need to end it extra term because you perform work, right? And this work was used to increase the potential of these atoms. So for this case, the phi will be mu1 plus extra term. So when the atoms locate or under the compressive region, the P is negative. So negative is positive. So anyway, you mu1 plus the extra term. And extra term is a compressive. Is a compressive times the delta omega. Omega is average atomic volume. Compressive stress times the delta omega. But on the other hand, if we talk about is a tensile stress, tensile region, then the chemical potential will be smaller than mu1, right? So it's minus extra term. So here P is positive, so you use a mu1 to minus a positive term. So if we compress to 3 atoms, the atoms at the no stress gradient region, compressive region, and tensile region, what are their chemical potential? Which one has the largest chemical potential? Will be atoms at the compressed region, atoms at no stress field, and atoms, the small one, will be atoms at the tensile region, right? Okay, so due to you observe the variation in chemical potential, so the atoms is definitely for sure will move from high chemical potential toward to low chemical potential. So in this case, it will be moved from compressive region toward to tensile region. So you will get the atomic flux. And if we switch to vacancy point of view, the vacancy will flow in the opposite direction from the tensile region toward to compressive region. So in order to quantitatively describe this atomic flux induced by the stress gradient, so first of all, we need to formulate the driving force. The driving force, as we mentioned, as long as you know the chemical potential term, you take the gradient minus gradient then you know the driving force. So we have a potential, right? Take the gradient and minus, you got the driving force. And just remark, compressive stress P is negative, tensile stress P is positive. And now you know the driving force. So atomic flux would be The first one is due to the concentration variation, so you use the minus diffusivity concentration gradient. The second term is due to the stress field, so we use the mobility, concentration, and driving force. And don't forget, this is positive. Negative become positive, so here is also positive, so mobility, concentration, and driving force. Driving force is omega times the stress gradient. So expressed like this. So now we want to give you more idea or more pictures about how atoms move along the stress gradient. So what we have is we have a location directed to the right-hand side, and the vertical axis means the stress. And as you know, compressive stress is negative, so we got a compressive stress here. The larger compressive will be more negative. The smaller compressive stress will be less negative. And the upper portion will be positive term, will be a stress. So the tensile stress. So we use a T to represent it. So now we assume the atomic flux of the atom is moved directly to the right-hand side. So when I hope you can draw in the stress field inside these materials, which can cause the atomic flux move directly to the right-hand side. So probably you will write what? Which means the stress gradient will be positive, right? Positive will be the stress gradient be positive. So can be high compressive region to low compressive region. High compressive region means more negative. C. Move to low, smaller, negative. So be this one to this one, or low tensile to high tensile, or compressive region to tensile region. Okay, so now you have some idea how the atoms moves along the stress field, right? Okay, so I'm giving you an example which happened on the polycrystalline materials. So if we have a polycrystalline material, which means we got many grains, right? So we focus on this grain, and this material suffer the shear force. We got a tau here. It suffer the shear force. And we can separate this tau becomes to this direction and this direction. And also this tau separate this direction and this direction. And this tau separate them this direction and this direction. So based on this idea, if you focus on this edge of this grain, it will suffer the compressive stress. And this will be tensile stress, right? And this will be compressive, this will be tensile. So based on this, the atoms, the mass transport will be from compressive region toward to tensile region. So you got the atomic flux go this way, and go this way from compressive to tensile. So you can expect this edge is going to move toward from this side, and this edge will be moved to. So the geometry of this grain will be changed during mass transport on the stress gradient. And so this is the very famous phenomenon we call the diffusion creep. This mass transport is due to the from the compressive to tensile region is a stress gradient happen inside your materials. But this is a atom's point of view, right? But if you want to switch to vacancy point of view, so we also have a vacancy flux, so all the values will be the same with the atomic flux, but the direction will be total upside directions. So you got the vacancy will be moved from tensile to compressive, tensile to compressive. Okay, so you got this kind of flux. And when you also can remember when we try to write down the vacancy fraction as a function of stress, can be expressed like this, and also is a vacancy formation energy, and because under the stress, so you need to end it extra turn be performed, extra work performed on due to this stress gradient, so be minus stress times the omega V. Okay? So the other example here or evidence would be if we have interstitials atoms inside our materials, when this interstitial suffer the stress field, and this stress field will lead or drive this interstitial move from compressive region toward to tensile region. So this is the driving force to drive this interstitial movement or this mass transport of these interstitials. Okay, so today we just ended here.